The topic of lesson 6 will be on analyzing beams as a subject that we study in strength of materials or mechanics of materials. And today I'm gonna analyze three different loading conditions on a beam. So the beam I'm gonna define is gonna be divided into um, three sections. Each section is an element, and all the elements are gonna be the same. So I have four nodes. So I'm going to number them 1, 2, 3, and 4. And definitely I have three elements, 1, 2, and 3. The first case that I want to study in here is, first of all, I'm going to say that I'm going to fix this end at node 1. And for the first case, I'm going to apply an F or a load of, let's say, 1,000 newtons downwards. And if my coordinates are like this, x and y, so this is going to be a minus 1,000 newtons in y direction for the load. And for the second so this is my first case of study. The second case is going to be this beam, that if I'm applying the same or if I'm dividing it correctly, the second case is going to be something like this. I'm going to apply a uniform pressure in the middle section of, let's say again, 1,000 Newton meters or Newton millimeters here. So this is my case number 2. And in case number 3, I'm gonna keep the constant or the uniform pressure of 1,000 Newton millimeters in here, and apply an extra pressure of non-uniform but changing in a slope from 1,000 to 2,000 Newton meters, and see the deformation and the results of my beam based on these three different types of loading conditions. So I have three different loading conditions. What you will learn in this lesson is how to modify your loading per analysis without needing to redefine your model, reselect your elements, and reapply the cross-section areas or real constant and materials. All you want to do probably is just change your loading conditions. So you will learn how to do this in this example. Plus, the other thing I want to teach is how to read nodal results. So let's say we're asked to find deformation in y direction plus rotation with respect to z axis for elements or locations on this beam of 100, let's say 100 millimeters apart. I'm gonna give this these spaces of 100 units or millimeters. So let's say we're asked to read uy, which is displacement in y direction, and rotation of each of these points, point 1, 2, and 3, or nodes 2, 3, and 4. That's why I'm planning to divide my beam into three sections with 4 nodes. And again, the material I'm going to use for this analysis is steel with elasticity of 200 gigapascals and Poisson's ratio of 0.3. And the element that I'm going to pick in order to do this analysis is going to be beam 3 with cross-section area um, of 12 times 12. So basically it's going to be square of 12 units by 12 units, which means my area moment of inertia is going to be 12 to the 3, as we had measured or calculated this similar thing in lesson 1. So with this, we can go to Ansys and do the analysis. Okay, we're in Ansys now, and we can start the calculation or analysis. The first thing I'm going to do is to go to Preferences and click Structural, and then come to Preprocessor. As always, define my element first. I'm going to pick element 3 or element beam 3 with the default options that are defined by ANSYS. I'm going to stick to the defaults. Come to real constants and add a real constant for my beam 3 of area 12 times 12, IZZ of 12 times 144, and the height of 12, which means the cross-section area is going to be 12 by 12, which is 144, and the height is 12, which means the width of my cross-section area is also going to be 12, which gives me square cross-section area. Click OK, close this window, go to Materials, and again, Material Models, Structural, Linear, Elastic, Isotropic. The elasticity is 200 gigapascals, and Poisson's ratio is 0.3. Let's go to modeling and create nodes as I had explained before. The first node is going to be located as at x0, y0, apply, and then the second node is at x of 100, the third one at x of 200, and finally I have a node at x of 300. Click OK. So all my nodes are made, and I can go to Elements, auto-numbered through nodes, pick the first and second node, I should have clicked apply, second and third apply, third and fourth. Okay, so my model is ready now. And because I used nodes and elements to create this model, I can skip meshing and jump to loads. Again, I can come here and make sure that I'm doing static analysis. Go to define loads, apply, structural, displacement. On nodes, so I click node or pick node 1, click OK, and make sure that all DOFs or degrees of freedom are 0. Now I have to come to force moments, because the first case that we're going to study here is a focused or a concentrated load on node 4. So I pick on nodes, pick node 4, click OK, and Fy of minus 1000. Click OK. My model is ready, so I can go into solution, solve, current ls, OK, and my solution is done. Can go to general post process, and the first thing I want to see is the deformation of my beam under this loading condition. So this is how my beam deforms under this loading condition. Counterplot, nodal solution, DOF, displacement in y direction, click OK, and as you see, the displacement in y direction for each based on nodal calculation is shown to me, and based on the conditions that we defined in node 1, there is no displacement in y direction. But basically it doesn't give me exact solution, so I don't know the results in or the displacement in node 2 or node 3 or even in node 4. I'm not very precise, so I can come to list results, nodal solution, degrees of freedom solution, y component of displacement, click OK. Now I see displacement for each of the nodes that I wanted to. So at node 1 there is no displacement in y direction, but at node 2 I have a displacement of minus 0.3858 times 10 to the minus 5, which is very small. But as we go further, in node 4 I have the greatest displacement in y direction. I can do the same thing in nodal solutions and instead of reading displacement in y direction, I come to rotation vector sum, click OK. So the rotation, or the angle of rotation, is given to me, which is again very small. And the other thing I want to read is reaction solution. Let's see, I want to read all the reactions. The only node that has reaction in here is node 1, because that's the only one which has constraint or a fixed end. There is an there is a reaction in y direction of 1000 equal to the load that we applied on node 4, and a moment of 0.3 times 10 to the 6. If you remember, the length of this beam is 300, and we applied a load of 1000 in here. 300 times 1000 makes 3 times 10 to the 5, which is equal to this, 0.3 times 10 to the 6. Now let's say we want to jump to case number 2. How do we do it? So basically we have to redefine our loading condition. What I want to do is I come to solution, go to define loads, and the first thing I want to do is to delete the load that I've applied on this node. So I come to delete, structural, force on nodes, and pick this node that I defined earlier. Click OK, and I can either pick all or FY, because I know that I only applied an FY in this one, but I pick all just to make sure every loading at that node is deleted. I can come to apply, come to pressure, and one thing you have to remember, that in order to apply pressure on a beam, you don't go to pressure on elements. Instead you come to pressure on beams, because this that we have defined is a beam. So I come to here, click on beams, and I pick the middle element, click OK, and I pick minus or 1000. The reason I'm picking 1000 is that this is pressure. So when you pick plus, or when you give a plus value for pressure, it goes toward the element. But if I pick minus 1000, it will go upward, so opposite to the direction of the element. So I pick 1000, and because I'm applying a constant and uniform pressure on this middle element, I can leave this value j blank, as it says leave blank for uniform pressure. So I can click OK, and as you see, I have a constant pressure applied to the middle element. So again, my case 2 loading condition is ready. I can click current ls and find the solution. Come here, and again, let's see how my element is being deformed. Shape is the same thing. Nodal calculation. Come to again, displacement in y direction. We can read the results in here, but again, let's go to list results, nodal solution, and read the displacements in y direction, which seems that the results are a little bit bigger than we got in the previous example, the previous case. We can read the same results for rotation, and again, the rotation values are a little bit bigger than before, because the load that we've applied is a little bit different. So let's go to reaction solution and read all the reactions which are in node 1. So again, we have an Fy, which is a little bit bigger now. This one is 0.1 times 10 to the 6. The length of this element here was 100 units, or 100 millimeters, and we applied 1000 Newton millimeters pressure on here. So 1000 times 100 gives 10 to the 5 newtons of force applied at the center of this beam, which is equal to this one. And if we say 1000 times half the length that of the beam is 150, so this gives the moment of the reaction which is applied, which is present at this end, which is fixed. Now let's apply the third loading condition. Because I'm not gonna delete any other loads, instead I'm just gonna add another pressure on this third element. So I don't need to define any load, so I come directly to apply structural pressure on beams again and pick this third element, click OK. Again, the first one is 1000, but this time I'm not going to apply a constant or a uniform pressure, so I pick or enter 2000 in here, and so this is shown to me. My model is ready. Come to solve, current ls, click OK, and my solution is done. I can come to general post-process. Again, if I want to see the deformation, it's basically the same. So I come to nodal calculations, click OK for displacement in y direction, and it seems that the displacements are a little bit bigger now. But how I can find it out is to come to list results, nodal solutions, displacement in y direction. Basically, it's true that the displacement in y direction is a little bit bigger now than the previous example. I can also do the same thing for rotation in y direction. I can see that as well, or actually it's rotation in z direction. And the other thing I can plot is the vector plot of rotation in y direction. So basically it's a vector that tells me in which direction my nodes are moving. But let's say we have defined enough elements. Instead of 3, we have, let's say, more than 3, let's say 100 elements defined for this beam, and we want to read or we want to list results for some results or data for each element. So basically I can come to element table and define a table. Click add, and for the first one I'm gonna say give me displacement in y direction per element. I'm gonna call it UI as it is. Click apply, and then pick rotation in z direction and call it RZ, and click OK. So I have a table of 2 columns for each element. I have displacement in y direction and rotation in about z-axis for that table for each element. I can close that and come to list results, find element table data, and I can pick UI and RZ that I defined earlier and click OK. So as you know, I have only 3 elements, 1, 2, and 3, and for each element I have displacement in y direction and rotation in z direction. If I had more than 3 elements, let's say I had 100 elements defined for my analysis, I could get 100 results and list them together and save this file or this list in a text form, and then load that text file in Excel and draw the graphs for it. So basically in this lesson you learned how to define element table. It's pretty easy and straightforward. You can just come here and add as many results as you want to this to your calculation or analysis, and then read the results for each element or from list results. But later when we get more advanced examples, I can explain more details and here how to use add items and multiply and find maximum and stuff. But so far you just get the idea of how you do that. And the other thing I want to do here, list results, reaction, solution, all items, and as you see things have changed compared to the previous 2 examples for this model. So basically this is the conclusion for lesson 6 of defining loads and different loads on a beam.